recording here. Oh, that's the wrong day. Okay. Last time I checked, I saw 3 people had signed on to WebAssign. It's pretty good. Remember, you do get the free trial, right? And so it's just log on, check it out. You've got a diagnostic test, right, which is really good for just kind of seeing where you're at, right? We're covering a lot of those basics that we need, right, in chapter 1. But it's just good to do the diagnostic test and see where you're at, how comfortable you're feeling. I'll count it as an assignment as well. So even though it's not called an assignment, I'll count it as an assignment. And then assignment 1 is also posted, and they'll be due next Friday and next Sunday, right? Both at midnight. So, log on to WebAssign. For your free trial, right? If you're already convinced that you're sticking around in the course, then may as well bite the bullet and just go buy the access code, right? Make sure that you buy it through the bookstore, and so you're not paying US dollars. That'd be brutal. Right, and so log on to WebAssign for your free trial, and the diagnostic test is due January 17th at 11:59, basically midnight. All right, maybe don't leave it to the last few minutes. That's probably not great. And then I made assignment 1. Is due on the Sunday, also at 23:59. So WebAssign does not make reminders for you on Moodle, right? But it will be posted when each of the assignments are due, and so you'll know well in advance, just like now. Okay. All right. Oh, what did I do on? Mercer. That's the wrong class. So I cleaned up, we talked about the test dates last day. I did clean up so the links are now just in the blurb, right? But it has things like my contact information, my office hours, our Zoom room. So this is our meeting ID. It's right there. And then here are the lecture videos are posted on YouTube. Okay. Did anyone check out?
Yeah.
Nice. You found it?
Yeah.
That is good. Yeah. Yeah. So, I mean, it looks better.
Yeah.
But some of the stuff in the background is not where it used to be. So it's harder I was like, how do I edit this course? But so what I did was I made just a WebAssign block, just so that you have them. I posted the slides here that we went through last day, and just kind of all the information. Here's our class key that you'll need to enroll. And I had to Google it. I guess enroll, you can spell it with 1 L or 2 L's. I don't know. I guess, yeah. Or yeah, British. But I can't remember which one's which. I think 1 L is British. 2 L's. Because the WebAssign uses 2 L's, but then it auto-corrected to 1 L. I don't know. Doesn't matter, it's not calc. So, but anyway, so I kind of revamped that. And then I posted the notes from last day as promised here. So you can have a look. All right. Any questions before we get started? Okay. So last day we were just talking about functions, and because we're going to keep talking about functions, there's not really anything to review. But today we're going to start by just outlining all the different functions that we might need, right? What do they look like, right? Because it's good to know. So, so just like if I ask you, hey, what shape is this? You tell me that's a circle because of this fancy notability option. It'll clean it up for me, right? What's that? Square. Or a rectangle if you're really finicky. I'm not. But anyways, so just like we are comfortable naming those shapes, right? We need to get to the point where we're comfortable talking about, well, I know an exponential function looks like this, right? I know a logarithmic function looks like this, right? Because then if we're seeing, if we've got information, right, we've collected data, for example, then we can say, oh, that looks like it could be modeled by this function, right? And so that's why we're developing this catalog of functions today, so that we can have them as the reference, just kind of going forward. You will have seen all of these. Nothing's going to be new in chapter 1, so, which is really nice. So, section 1.2 is called Essential Functions. They are essential. I guess I didn't write that very nice. The first essential function we'll talk about is our most basic function, a straight line, right? So a linear equation, y equals mx plus b, kind of our go-to, probably the one that we're the most comfortable with, right? And so a linear function it looks like, no surprises here. Let's see. Doo-doo. All right. Can have a positive slope, a negative slope, but in general, just a straight line, of course. So a linear function, there's two ways actually to talk about a linear function. The slope-intercept form, y equals mx plus b, right? Where m is the slope and b is the intercept, right? Slope-intercept. Where m is the slope and b is the y-intercept. If we don't know what the intercept is, but we know another point, right, it's going to be easier to just use the point slope form. Okay, and so the point slope form is y minus y1 equals the slope m times x minus x1. Right. Where we know m is the slope and the point x1, y1. Right. So depending on what information you have, if you imagine x1, y1 being the y-intercept, right? At the y-intercept, x is 0. So then you have mx on the left or on the right-hand side, right? And then you've got y minus y being the y-intercept, or y1 being the y-intercept, right? You can rearrange that, right? Call y1b, right? And you get the same thing, not surprisingly, right? And so they're the same. In fact, I would say that the point slope form is actually more versatile, right? Because from the point slope form, we can get to the slope intercept form, right? Because it's just a special case. Okay. All right. So from a straight line, we move into polynomials. Polynomials are actually kind of a big set of functions, right? It's a lot of things. But polynomials in general will follow this format. We use capital P of x, for example, is a sub n times x to the power of n plus a sub n minus 1 times x to the n minus 1 plus all the way to a2x squared plus a1x to the power of 1, but I'll drop it and I need a little bit more room, so I'm just going to scoot this over here. Plus a sub 0, technically times x to the power of 0. Anything to the power of 0 is 1, right? So it's just a sub 0. Okay. This is a polynomial in general, right? And so if you have a polynomial like this, right, you're going to have a leading term, right? And so here, this is the leading term. Right? And each of those little blocks are terms. Right? Each term is going to have a coefficient, right? The coefficient has to be an integer, right? A positive integer, or I guess negative if you end up subtracting. But if it's 0, right, that just means that that term goes away, or term goes away. And so that's an option too. So you don't have to have all of them, right? Coefficient can be 0, making it drop off. So the leading term, that's the one that we're kind of concerned with, right? Because whatever n is, right, the power of x, right, that's your highest power in your polynomial. And so that's the degree of your polynomial, right? And so n is a non-negative number or integer, right? And a sub 0, a sub 1, a sub 2, all the way up to a sub n minus 1, a sub n are constants called the coefficients. The leading term will be the term with the highest power. Will be the term with the highest power. Okay. The highest power is the degree of that polynomial. The highest power is the degree of the polynomial. as a fact, right, any polynomial, so any straight polynomial is just going to have a domain of the set of real numbers, right? So from negative infinity to positive infinity. So it can span, or it will span, the whole set of numbers. Okay, so all polynomials have domain. Remember our fancy R? That's good. Sorry, so someone left. See you later. So all polynomials have domain, the set of real numbers, right? Which I'm going to say is also negative infinity to positive infinity. Remember to use those round brackets, right? Because infinity isn't actually a number, right? It's kind of it's a feeling. No, it's an idea. Right? And so, so that's why we have to use the round brackets. In the simplest form, right, y equals x squared, that's a polynomial. In fact, y equals x is a polynomial, right, degree 1. Okay. But if we talk about y equals x squared, right, then that's the simplest form. So y equals x squared is a polynomial. Degree 2. Oh, turn my 2 into a circle. Y equals x to the 3 is a polynomial, right? So these are the most basic polynomials. Degree 3. Okay. The behavior of polynomials in a graph, right? Because that's what we want to know what it looks like, right? X squared we know is a parabola, right? Nice parabola, probably the second most familiar function that we kind of feel comfortable working with, right? And so, and then x to the power of 3 is this kind of wheel, right? So we should know what that looks like, probably a little bit less familiar, right? But still kind of feeling pretty good. In fact, any even degree, right, is going to have that parabola shape, and any odd degree is also going to have that, I don't know, what do you call it? Like that. So they'll all have that type of shape, right? And so even degrees on the XY plane are going to look something like that, just in general. And odd degrees will follow the same shape as x to the power of 3. And just kind of I guess I should have smushed it more. That's some odd degree, depending on how high it is. But the shape is all we care about. Okay? And so what's nice about knowing what an even degree and what an odd degree are going to look like, right, is that even if we start doing crazy things like dividing a polynomial by a polynomial, right, usually that gives us some asymptotes and there's some weird stuff going on, but the end behavior will always be the same. right? And so you don't really care about what's happening in the middle. The end behavior is what we're going to be kind of more concerned about, right? And if you have an even degree, then it's shooting up to the top, right? And if you have an odd degree, it'll behave like this, right? And so, I wonder if we talk about it later. No, it's not for a while. I'll put it in here. So, even in more complicated functions, we will still know the end behavior will behave the same for even and odd functions, right? So now we're talking about the end behavior of even and odd functions. Oops. For even degrees, oops. We'll have something like this, right? Just like we're used to. And of course, x squared, we know it just connects, right? But we could have something in it, as long as we have the highest power is an even power, then we know that at the end of the day, right, once it's done doing its little jiggly thing, maybe there's some asymptotes, maybe there's some weird stuff going on, right? At the end of the day, that end behavior is just going to be pointing up. That is assuming that the coefficient is positive, right? If the coefficient is negative, then it's pointing down, right? And so, so this is if, and I'll use a sub n is greater than 0, right? So a sub n is your leading coefficient. Okay. Maybe I'll sneak that in up top here where we talked about the leading term. A sub n is the leading coefficient. You can figure that out probably, but it's just nice to have it in there. Huh? So, and then, or it'll look like this, right? The end behavior if a sub n is less than 0. Got glitchy here. There. Same thing for odd degrees, right? Never mind the middle part. For odd degrees, the end behavior will be something like this if the leading term is positive, and the opposite if the leading term is negative. Or, let's see if I can get these straight. If a sub n is less than 0. Maybe I should put little ... Anything can happen when you work as a team. Isn't that song, that Lego movie song? Anything can happen. Everything is awesome. I guess anything can happen also works. I'll write to the Lego movie writers. All right. So having a good handle on those polynomials is going to be good. We'll move on to power functions. There's a couple of different power functions. So in general, a power function looks like f of x is x to the power of a. Oh, that looks like 9, but it's an a. Where a is a constant. It's an a. There's a couple of different options for a, right? So a can be just an integer, right? A positive integer. We can move into negative integers, right? So we'll talk about first one, if a equals n, where n is a positive integer, well, x to the power of n, that's what we were just talking about, right? So where n is some integer, right? Some positive integer. And so now we're just in a polynomial, right? And so here, this would be just a typical polynomial. Polynomial, which we just talked about, right? So a polynomial is a power function, right? It's a special case of a power function. Our other option that we'll talk about is what if a is 1 over n, right? Where, of course, n is the same positive integer, right? So now we have a to the power of n. Well, that means that we have f of x is x to the 1 over n, but we know that that's our shortcut for taking the nth root of something, right? If I have to take the 234th root of x, I would rewrite it as x to the power of 1 over 234, right? So that's my shortcut. So that's the same as taking the nth root of x, and we just put the n in the little hook and move on. Right. Usually I'm moving from the bottom one to the top one because that's how I'm going to do my calculations, right? It's going to be easier to work with. Right. So depending on if n is even or odd, right, the shape of it is going to be a little bit different, right? And so if n is even, right, the general shape is going to be something like this, right? Starting at 0, just kind of notice here that the domain is only from 0 to infinity, right? And so we can't have any negative outputs, and that's all right. Yeah. If n is odd, then we can have negative outputs. I guess I should do both sides, x and y, and it'll look something like, I am really bad at drawing curves. I feel like there was a time in my life when I was pretty good at it, but now, well, they are what they are. So, same thing, right? If you have an even root, right, then you know that, well, it can't be my domain, so my input of x, sorry, I think I said output, but the output can't be 0 or less than 0 anyways, so it's still safe. I was safe in either way. But our inputs, right, have to be positive. We said that last day, right? If we have the square root of x, our domain, right, we can't take the square root of a negative number. And so that's what we're seeing here. Yeah? And so, in fact, we can't take the nth root where the n is even of a negative number. Right? We just can't. So it extends to any even root. For odd roots, we can, as we can see here, right? It'll just give a negative output. Our third option that we'll talk about is if our power a is -1, right? We could extend it to any negative integer, right? But we'll talk about -1 because remember, if you've got the power of -3, for example, you could write it as -1 times +3, right? And then go from there. And so we've got f of x is x to the -1, which we know is just 1 over x. Right? And again, typically, the way I use this is I am going from the bottom, so I have 1 over x or 1 over x squared or whatever. And then I want to bring that to the top, right? So I want to bring it to the numerator so I can cancel those powers. And so I rewrite x. So 1 over x to the 3, I would rewrite as x to the -3, for example. Right? And what does it look like? Well, we've got that nasty asymptote in there, right? Because we can't divide by 0, right? And so we've got something that looks like that. I just realized there was one little thing from the notes last day that I did not do. What was it, I wonder? It's one little thing. Anyways, I'll talk about it next day. How about I'll remember. I didn't bring them. It's in there, but I'd have to find it. Luckily, Steve told me that he doesn't talk about symmetry until later. So if you have an odd or an even function, he said, oh no, I just do that later. So, okay, good. Cut out a bunch of my notes from last day that we didn't get through. I think that's why I was so excited to start 1.2. Anyways, rational functions. Now we get into kind of the nasties. Rational functions is a ratio of two polynomials, right? So a polynomial divided by a polynomial. And so a rational function is a ratio of two polynomials. So it'll look something like f of x is p of x over q of x. Now you're dividing, right, by q of x. And so your domain, well, you have to make sure that q of x can't be 0, right? So it gets a little bit more complicated. So we'll not really go into it. today, right? But we will get to rational functions and just know that it's a polynomial divided by a polynomial. And we also know the end behavior behaves like this, right? We will have some asymptotes and some weird stuff going on in the middle, right? But as long as you're able to identify your highest power, then you know the behavior, the end behavior. We'll move on to algebraic functions. This is kind of covers all of those random functions that you see. So you've got x squared plus 4 minus the square root of x minus 1, all those weird things, right? So just a hodgepodge, a combination. All those would be algebraic functions, right? Because they're just strung together by algebraic operations, right? And so constructed using algebraic operations, so addition, subtraction, multiplication, division, and roots. Right. Square root being the most common, but we can take other roots. Starting with polynomials, right? So at its base, there's a polynomial in there somewhere, and then we manipulate it, probably add or subtract other polynomials, right? Divide polynomials, all that kind of fun stuff. So here, when we take a polynomial divided by a polynomial, right, that's introducing an algebraic operation to two polynomials, right? And so a rational function is an algebraic function, right? It's just a special case. And so a rational function is an algebraic function. This one's not that helpful because the graph can look basically like anything, right? And so you can have, you know, first part looking like a nice, I don't know, reverse logarithm maybe, and then it gets a little crazy around 0, maybe because there's some asymptotes going on, and then I don't know, maybe it curls off like an x squared, right? And so it depends on the combination, but there's really no way of knowing what it's going to look like, right? Have you guys used Desmos before? Desmos? Yeah, cool. If you're graphing a function, so it's a free app. Let's see if I can find it here. There. Looks like this. You're going to use Maple in the labs, right? But sometimes it's just helpful to know what a function might look like, right? So if we do things like x squared, right, it'll look like this, and we can kind of look at points on here and try to figure out what it's going to look like. And then maybe x to the power of 3. Where is it? Where's the power? Oh, functions. Anyways, you can do a ton of other stuff. I was wanting to. Oh, thank you. There. 3. I'm seeing a squared and b squared. That doesn't help. Thank you. So things like that, right? Later on, we might want to find the intersection of 2 points, right? And of course, you're going to do the work by hand, right? Because that's how we do it on tests. But it's just nice to have something to quickly be able to check your work, right? And so Desmos is free, and you just download it. I don't even have an account, I don't think. I just have it on here just so I can check stuff. Sometimes you might need to zoom out to see what's going on, right? But pretty fun. Check it out. I would encourage you to use it to kind of see what's going on, check your answers, check your work. Last set of function, I lied. Last set of hard functions. Algebraic functions are just kind of this vague thing, right? It's any hodgepodge of polynomials and such, right? And so, but trig functions, I know, no one likes trig. That's okay. Including probably myself. I might like it more than you, but still. Trigonometric functions. Did you know that any function can be represented as a combination of trig functions? What? We're not going to do that, obviously. But for trig functions, I know, at least for me, when I kind of got into calculus, I had a heck of a time keeping track of my radians and degrees. You know, you have to change your mode on your calculator. For us in calculus, right, we're just going to stick with radians. I know, everyone likes degrees. No one likes radians. But we're going to stick with radians unless it's clearly indicated, right? You move 36 degrees, whatever, right? But usually they're all just going to be radians. So you can change your mode now and set it and forget it. Okay? So trigonometric functions, as a note, oh, I'll even do it in a different color. How about? In calculus, we will always use radians except when otherwise, and it should be clearly indicated. Oops. For symmetry, I'll make my star blue as well. So we're not going to talk too much about trig functions today because we will use them later. And we'll talk about sine, cosine, and tan, and then, or tangent, and then the others are just inverses of those. So we'll talk more about those when we get into inverses. How about? Okay. So sine of x, if we're working on in radians, right, well, it starts at 0. And then we just kind of bobble our way through here. Make my line a little bit longer. Remember, it starts to repeat itself at 2 pi. Goes as far as 1 and -1. Unless we've manipulated our sine function, right? But the basic sine function starts at 0 and has a period of 2 pi. Period is 2 pi, right? How long does it take for it to start over again? We use trig functions to model any sort of cyclical behavior, right? So the sun, the moon, the stars, tides, waves, right? So all these things that are kind of coming and going, coming and going, coming and going, right? They're modeled by sine and cosine functions, or maybe a combination of the two, right? And so sound waves, right? Vibrations, all those things. So cos x is the other one. If you're like me and you have to think about it that way. Also going between 1 and -1, but cos x starts at 1, right? And then after 2 pi, it'll be back at 1, right? And so it starts up here. And at 2 pi, it'll be back at 1. So the period is also 2 pi. How I end up remembering it is that it falls in alphabetical order. So cosine starts at 1 and sine starts at 0, right? Whatever you have to do to kind of remember which one starts where, doesn't matter to me, but that's what I do. C before S, C starts at 1, S starts at 0. Fine. And then there's the tangent of x. Tangent of x is just sine x, oops, over cos x. So it's going to look a little bit strange, right? Because now we're dividing by cos x, but our divisor, right, the denominator can't be 0. So wherever cos x is 0, right, we've got these asymptotes, right, these holes and gaps, right? And so cos x is 0 at pi over 2 and 3 pi over 2, which is why we'll have asymptotes at those points, right? And so here, I'll put pi over 2 and 3 pi over 2. And let's see if I can do this. I did not set it up very well. Here's negative pi over 2. Got smushed. But anyways, it's going to look like this. Nope. One curve, fine. 2 curves, 3 curves, no thank you. Anyways, in general. 3 pi over 2 should probably be scooted out way more. And the period of tan x is just pi. Because we only have to move out pi radians to get to the next, to start new. Okay. Any questions? No. How about, and I'll just say cosecant of x, secant of x, and cotangent of x are inverses of the original trig functions. Right. We're not going to talk about those quite yet. And I'll probably do my best to avoid them. I don't like them. We've got our hands full with the original trig functions. Right? They'll come up, right? Because they are the inverses after all. Right? All right. Let's move on to something lighter. Exponential functions. Exponential functions, in general, look like f of x is b to the power of x, right? Where b is a positive constant. Where b is a positive constant. We spend a whole section talking about exponential functions later. And so I'm not going to talk too much about it here, right? But just in general for our catalog that we're developing, right? Exponential functions, they model growth. So just kind of exponential growth. If our b is greater than 1, almost said 0, but greater than 1. Right, so as long as we've got a large enough base, right, larger than 1, then we've got this exponential growth. If we have a base that's less than 1, then we've got decay, right, but it's going to look kind of the same. So exponential functions model growth when b is greater than 1, right, and decay when b is less than 1. So their graphs are going to look like this. This is if b is greater than 1, right? We've got this growth. XY plane. And then we've got this decay model if b is less than 1. All right. This is our last function that we're going to add to our catalog. Okay, and it's the logarithmic function. The logarithmic function is just the inverse of the exponential function, right? And so we kind of use it to undo an exponential function. And what you might remember is if you've got an x in the power, right, the only way to bring that down is to use logs, right? And so that's why we have to talk about logarithmic functions as well. Logarithmic functions. Logs used to be really, really hard to solve. Right now, we've got a button on our calculator and it's fine, but they used to be really very difficult. And so, especially if I told people like my grandpa that I was doing a math degree and he said, oh, so logarithms and stuff. It's like, yeah, I guess. But for us, right, logs aren't that big of a deal. So I was like, yeah, sure, we deal with logs. But But yeah, so they used to be this kind of big thing that you could not handle, but now they're so easy because we've got calculators, we've got Desmos, we've got Maple, we've got all these computers working for us. But in general, they're going to look like f of x is log base b of x. I'll just say where b is a positive constant. Where b is a positive constant. Logarithmic functions, oops, are the inverses, I guess, of exponential functions. Right. So log base b of x is the inverse of b to the power of x. Okay. So they go hand in hand. And remember, the inverse is just how we undo another function. And in general, a logarithmic function is going to look like, oops, looks like a B. It's going to look like this. Any questions? So, of course, if you're flipping through the textbook, right? By that I mean the ebook. Then, of course, the textbook kind of goes through and does examples of each of them, right? But we're reviewing here, so and I do find that it's helpful to just have it all condensed sometimes, right? So you just flip back to it and kind of, oh, that's what it looks like, right? Oh, and that's what I'm expecting it to behave like. Any questions? So that's the end of our catalog. Right. So now, just keep going. Just keep swimming.
Base bx.
Yeah.
The inverse of bx.
Is b to the b to the power of x.
Okay. But what's that thing where it's like log base a x equals y, and that is x equals y to the power of, or x equals a to the power of y.
So if you have y equals log base a of x, okay, then the inverse of y is going to be a to the power of x. Is that what you got? No?
It's okay.
But this is the inverse of y, and we haven't talked about, so it may be, because we'll go through it more when we talk about inverses, but we haven't talked about inverses yet. And so remember, the inverse is where you replace your x's with y's, right? And then we solve for y, and then that's what we've solved for is the inverse, right? But we're getting there. But So then we'll do an example where we unravel this one. How about? For now.
Is it worth me checking like the x to the y and we check that it is the same?
So to find the inverse won't necessarily be the same, right? But to find the inverse, then we swap our two variables, right? And then we solve for the y. So then we kind of rearrange it and solve for the y, because then that new function that we found would be the one that kind of undoes the original function. Right? So we'll save that for next week, though. Right? But yeah, so inverses, once you kind of get the hang of it, they're pretty fun. Right. All right. Section 1.3 is called new functions from old functions. So we know some functions that we just established, right? Now we need to be able to talk about, okay, well, if I have some old functions that I know what they look like and what they behave like, what do these new functions look like? Right, so new functions from old functions. I was so relieved when Steve told me that he does not cover the graph transformations, the stretching, the reflections, all that. I think you're all kind of, all right, that is a relief, right? So I was thrilled. But if it were to come up, if you're working on something and you're not sure how this graph would behave if it was multiplied by a negative number, for example, then first go to probably check it in Desmos, and then you can just see what it looks like, right? Or this would be the section where it goes through and talks about, okay, how do we do reflections? How do we shift a graph? How do we transform it? So graph transformations. But I will say this, we won't spend any time talking about transformations. So we won't spend any time talking about transformations. Transformations of functions. Just to keep my options open, I'll say we will revisit the topic as necessary. Apparently not necessary at all. Okay. Steve's taught this course a ton of times, and so whatever he says, I'm saying great. So, all right. We will revisit the topic as necessary. Okay. Just so you have a note, right? If needed, this is more if you're working on your own, so you won't need it for the tests or anything like that. So don't worry. I'm not out to get you guys. If I say you don't need it, you don't need it. But if you need it for whatever reason, this is where the textbook discusses shifting, stretching, and reflecting graphs. Right. I'll leave it at that. Phew, right? I don't know if you guys remember kind of shifting, stretching. I can't even remember. I think it's the x plus h, x minus h. It behaves differently than what you think it's going to do. Anyways, I have to tell myself it's whatever I think it is, it's the opposite of that. But anyways, doesn't matter. What is important from this section where we're trying to develop new functions from old functions is function composition, right? And so we can add functions, we can subtract functions, divide functions, add functions. We can also compose new functions. And so we'll start with a combinations of functions. So we'll pick two arbitrary functions. So two functions, lowercase f and lowercase g. Usually we use lowercase for function names, unless they're special, like a polynomial, right? We use capital P, weird stuff like that. But just in general, so two functions, f and g, can be combined to form new functions. The first one being, well, if I have f plus g of x, I can rewrite that as f of x plus g of x. That's fine. So the two functions added together are in fact the two functions just added together. Same thing with the subtraction, f minus g of x is just f of x minus g of x. Same thing, f times g of x is f of x times g of x. Okay. F is going to have a domain and g is going to have a domain, right? And so if we call the domain of f a and the domain of g b, right? Then all of these will have the domain where the two domains overlap, right? We can't have one without the other. And so it's the intersection of A and B. And so these functions each have a domain, right? So if capital A is the domain of f, and capital B is the domain of G, then the domain of f plus g of x, f minus g of x, and fg of x is the intersection right, which you're going to read as A and B. Do you guys remember the intersection and the union, right? And, or. Right. Essentially, the domain of the combination, right, is going to be just the overlap of the old domains. The special case is if we have f over g of x, right? Well, that's f of x over g of x. It follows the same setup as the others, right? We can just rewrite them, kind of transfer the x inside, I guess you could say, right, onto both of the functions. And so here, now we're dividing, so now a little alarm bell should go off in your head saying, oh, I can't divide by 0, right? And so now the domain is going to be a and b, right, the intersection of a and b, but also making sure that g of x is not 0, whatever g of x is. Right? And so here, since g of x cannot be 0, our domain we can write as, let's get a little crazy, curly bracket, we'll use set notation, so x, have you guys seen the is in the set? A and b such that g of x is not equal to 0. Is in the set A and B such that, or given that, g of x is not equal to 0, right? So function addition, subtraction, multiplication, division, that's all fine. Things get a little bit more fun if we get into what's actually called function composition. So where we compose a new function by sticking functions into other functions, right? And so I'll put it on a new page. Given two functions, f and g, the composite function f, and then a little open circle, OG, right, which is just thread f composed with g, right? I usually just end up reading it f of g because it turns into f of g, right? Because we're plugging in g of x where we would have had an x, right? So f composed with g is defined by f composed with g of x is f of g of x. Order matters, right? So notice that g composed with f of x would be g of f of x, which is not necessarily equal to f of g of x. So order matters in this case, right? The first one, that's your main wraparound function, and then the second one goes inside there. And you can compose more than 2 functions, right? You can have 3, 4, 5 functions, and then so just the order. Or if you have f composed with g, composed with h, composed with I of x, that's going to be the same as f of g of h of I of x, 1 bracket, 2 brackets, 3 brackets, 4 brackets. That kind of thing. So you just keep, what are those? Russian dolls? Did you guys see that show, Russian Doll? I just watched it recently. It's pretty good. Pretty fun. Anyways. So, right, you can compose as many or as few functions, at least 2 though. All right. I will put a little pink square around this original one because function compositions are going to be pretty important. Gets tricky when we start talking about the domain, right? Because while f is going to have a domain, g is going to have a domain, but now g is going inside of f, right? And so what we do is we have to make sure that, well, we know we have to abide by the domain of g, right? Because g is in there. So whatever is in the domain of g, right? That goes in. But then also we have to pull out any points in that domain of g that don't fit in the domain of f, right? So the domains get a little bit tricky sometimes, right? If you've got a combination of a square root and a fraction, for example, right? And so gets a little bit nasty, but the domain of f composed with g is the set of all x in the domain of g such that g of x is in the domain of f. I usually find it pretty helpful if you just have a look at, well, what's the domain of f and what's the domain of g, just so you know what you're dealing with, right? If the domain of f, the wraparound function, is all real numbers, then whatever your domain of g is, that's the restriction, right? Because f can take on any numbers, right? And so just knowing what the domain of f is, right, is going to help you identify, kind of chisel down the domain of f composed with g. All right, let's do an example. It's example 6, and I just steal these from the textbook. If f of x is x squared and g of x is x minus 3, find f composed with g and g composed with f. So I'll give you guys a little bit of time to do that while I clean this up. Okay. Even if you're not quite finished, we'll get started. So f composed with g, we'll start there. So f composed with g of x is the same as f of g of x. Hey, my phone. So what that says is, well, f is going to be wrapped around g of x, but g of x I can replace with x minus 3, right? And so it's going to be f of x minus 3. You can work from the inside out, or if you prefer to work from the outside in, that's fine. I kind of tend to do whatever is easiest, right? So what I mean by that is you can replace f, the wraparound function, by x squared, right? And then so you've got g of x squared. Just depends on what's easier. So now I'm plugging in x minus 3 wherever I see an x in f of x. And so what I have is I have x minus 3 squared. If we try g composed with f of x, well, that's g is the wraparound function and f of x is on the inside. Which means g is going to take f of x, which is x squared. Right, so wherever I see an x in g, I'm going to replace it with x squared. And so what I have, g of x is x minus 3, and so x squared minus 3. Here, it's pretty clear that x minus 3 all squared is not the same as x squared minus 3, right? And so clearly, f composed with g of x is not equal to g composed with f of x, which we already said, but it's nice to see some proofs in the pudding. If we had to talk about the domain, it didn't ask for the domain here. What's the domain of x squared? Well, x squared is going to take any value of x, right? So the set of real numbers. And then x minus 3, again, there's no illegal math going on in there, right? There's no square root, there's no division. The set of real numbers again. So if I put the set of real numbers into something where the set of real numbers is allowed, my new domain is just the set of real numbers. So that's why they didn't ask for it, because it's pretty boring. How about instead, we'll have a look at if f of x is the square root of x. So now the domain of f says that, well, I can't take the square root of a negative number, so I have to keep that in mind. And g of x is again the square root, but of 2 minus x. So now 2 minus x can't be a negative number. Find each of the following functions and their domains. f composed with g of x, g composed with f of x, oops. Oh. I'll read that later. Oh yeah, f composed with f, you can do that. Plug f of x into f of x, right? It's kind of snowballing itself, right? And then finally, let's do g composed with g of x. See what's going on there. Right. So I want you to take some time, work through these, thinking about the domains and kind of arguing your way to what the domain might be. I know you're probably definitely not done, but that's all right. We'll get through these. So f composed with g of x, we'll start there. Well, that's the same as f of g of x. G of x, so it's f of the square root of 2 minus x. And then f of x was the square root of x. And so we've got the square root of the square root of 2 minus x. The square root and then another square root is the same as the fourth root, right? And that's if you convert the square root as, so the square root of x to x to the 1 over 2, right? Then take the 1 to the power of 1 over 2 again, right? And then you get 1 over 4, which, so this is just going to turn into the fourth root of 2 minus x, right? It's an even root, and from our catalog, right, we know that the domain of an even root, right, we can't take the even root of a negative number, right? And so we know should we get fancy here? May as well. X, and whenever it's understood, or it's just understood, if we just say X, X is in the set of real numbers, right? And so X is in the set of real numbers such that 2 minus X is greater than or equal to 0. Right? X is everything, assuming that 2 minus X is greater than or equal to 0. Right? And so solving the 2 minus X is greater than or equal to 0. Now you could have done this on the side and then figured out what your domain might be in proper notation, whether that's interval notation, set notation, right? Doesn't matter. But that means that that's X such that negative X is greater than or equal to -2. Remember being careful with the inequalities, right? If you're dividing or multiplying by a negative number, then it switches the sign, right? And so here, that's why I kept my negative X there. And just to keep going, since we're on a roll here, X must be less than or equal to -2, which I'll just write as 2. Right, and then I'll fill in the rest, X such that. So X has to be less than or equal to 2. G of X had the same domain, right? And so because 2 minus X has to be greater than or equal to 0, right? And so X has to be less than 2 to make it positive, right? Because 2 minus 3 is too big, it makes it negative, right? So they have the same domain, and so our domain is the set of X such that X is less than or equal to 2, or if you prefer, -infinity up to and including +2. How about G of f of X? G composed with f of X is G of f of X. So now I'm plugging f of X, which is the root of X, into G. So G, oops, double root. G of the square root of X. Now, wherever I see an X in G, I'm going to replace it with the square root of X. And so now I've got the square root of 2 minus the root of X. We need to know the domain of the inside function, right, which in this case is f of X. Right? And then we need to talk about, okay, well, as well as satisfying that domain, it also has to satisfy the outside functions domain. Right? And so we need X to be greater than or equal to 0. This is the domain of f of X. Yeah.
I was just wondering, would we be able, like, is it allowed to split them up? We can do the square root of 2 minus the fourth root of 1.
No, the square root only transfers onto multiplication and division. So just the same as we're not allowed to just take the square inside the brackets, think about it the same way, but for the roots, right? So if you're adding or subtracting in there, it's a no-go. But if you're multiplying or dividing, you're allowed to do it. Right? So that's a really good question. Yeah. Adding or subtracting in there, then all bets are off. Can't do it. Multiplying or dividing, then you're allowed. So we need to satisfy the domain of f of x, which is just x has to be greater than or equal to 0, right? It has to be positive. But then also we need 2 minus the root of x to be greater than or equal to 0, right? That's the domain of g of x. Oops. Right. Not really g of x. I'll put kind of air quotes around g of x, right? The domain of g of x is different, right? But if I'm thinking about it as the outside function, and it's a little bit easier. So the domain of the outside function is that 2 minus root x also has to be greater than or equal to 0. And so we can solve for negative root x, just taking it nice and slow, right? At least in the beginning. And so now I'm dividing or multiplying by -1, it doesn't matter. They're the same, right? Adding and subtracting are the same, right? Subtracting is just adding a negative number. Right? Multiplying and dividing, they're the same. Right? So they're all the same. So now I'm multiplying or dividing by -1, and so I get root x must be less than or equal to 2. Well, we need to satisfy both. So do you mean the x greater than or equal to 0 on the top?
No, like writing the negative square root of x is greater than or equal to -2.
Oh, I'm showing more work than you would have to, right? It's just to remind myself that I have to flip the sign. But if you're okay, if you're comfortable just going from the top to the bottom, that's fine, right? I'm okay with that. Just making sure that you switch that sign. And then if we want to shake out an x, right, because we want to know how x behaves, then I can square both sides, and I get x must be less than or equal to 4. Right.
So the root which was overall on the, I mean, like it was the whole root 2 minus under root of x.
That's right.
And that the whole root got on the 0 on the other side, on the right hand side.
No, because all we're concerned about here is that so what we're doing here is that we're making sure that, hey, where's that pointer thing?
Oh, as the back.
Is that this inside here is positive, right? So that's what we're doing here.
So we will not be using the other root which is on the whole of the term.
This other root?
Yeah.
No, we don't use it so much as it just tells us that this has to be positive. So that's where this comes from,
Okay.
right? That we have to have a positive value in there. But otherwise we just kind of ignore it for a little bit. So it's what tells us the restrictions on the domain, but then we focus on the inside of it. So the combination of these two domains, right, both of them have to be satisfied. So we know that x has to be greater than or equal to 0, but also less than or equal to 4. So we've got this closed interval from 0 to 4. And so our domain for g composed with f of x is, well, x is between 0 and 4 inclusive, or just the closed interval 0 to 4. if we have to do f composed with f of x, right? Feels a little weird, right? But we're just stuffing f into f. We can do it 5 times over if we want to. Gets a little weird though, right? But that's the same as f of x, which is f of, and f of x is the root of x. And another root on top of that, right? We saw that that becomes the 4th root of x. We know the domain of f of x. Well, that's just x greater than or equal to 0. And we're stuffing it into a function that has the domain x is greater than or equal to 0. So together, their domain will just be x is greater than or equal to 0. Right? And so the domain, which I'll start probably writing just d colon, is from 0 to infinity, inclusive of 0, right? Or x is greater than or equal to 0. And let's just start g of x. Oops. Which looks like g of x. G of, and then g of x is the square root of 2 minus x. So now I'm putting the square root of 2 minus x wherever I see an x in g of x. So that becomes the square root of 2 minus the square root of 2 minus x, right? Gets a little hairy. I want you to work out the domain on your own. And for next day, I want you to read, what did I say here? 1.4 and 1.5, right? Should be pretty familiar. And we're going to get into 2.1 for Thursday next week, right? But you've got a little bit of time, but at the beginning of the term, we feel like we'll get all our readings done, all that fun stuff, right? And so remember, the ebook is for free once you sign up, at least for that, the free 2-week trial, right? You should have access to the ebook as well through there. All right, any questions?
So the answer for this one is x greater than equal.
I'll just turn this off first.
Okay.
Yeah. No other questions besides confirming it? All right. See you guys on Tuesday, I guess. And labs start next week, right? So starting Monday morning or whenever you have them, labs are on. See you guys later. All right.